Hi, I'm DJ Ware. On this episode of the CyberGizmo, I'm going to be delving into something called Linux protection rings. Not protection rackets, but protection rings. Let's talk about it right after this. So one of the things I wanted to do when I started this channel was to, come around and do some discussions about some of the internals in hopes that whether you're just using Linux to, go to the web, do some banking, read a book, watch a movie, or whether you're actually using it for development. Now, if you're a developer, you probably already know these things. But if you're wanting to get into system administration, you want to understand a little bit more about the internals. So I thought I would take a number of topics, and I'll talk about that at the end, the ones I want to do, and see if this is of interest to you. So today I'm going to be talking about protection rings and what those are. So kind of a background, what are they exactly? So in the old days, we had system supervisory programs, which were basically supervisors and not operating system. They call them executives, and they didn't have any way of protecting themselves from an application. Of course, there was the built-in protection, which they could only run one job at a time. So if it crashed, it just took the machine down, and you got to read what they called a warm IPL, initial program load, in order to get it back up again, because it usually took the executive with it. And what was felt at that time was we needed some way to protect the kernel, or the operating part of the system, from the application, so that if the application crashed, that it wouldn't take the system down with it. And that became important when we started having multiple users that were working off the same computer at the same time. It wasn't very nice to crash the system on somebody else that was in the middle of writing a document and not being able to save it and have the system go down on you. So the idea, though, was that the applications would have access control structures to the operating system. There would be ways for it to make requests that the kernel could then work on. So there wouldn't be the user application wouldn't be making direct calls into memory. The danger of that always is if you happen to jump out of your assigned space into someone else's, you could do enough damage. You could be writing over a code area, a code block in memory, and you could cause the other program to crash. But Linux, Unix, and Windows all support a two-mode ring. And one of those rings is user land or user space, and the other one is kernel or system space. Some people think that Unix came up with this idea. Some people think that Windows came up with it. Some people think that Intel did it. If you thought any of those, you're wrong. The Multics came up with it. And they actually invented the idea. Their operating system actually had 64 rings in it. But let's talk about that for a minute. So they invented the use of protection rings in 1964. This was well before the System 360 was built and the OS 360 was designed. But even that had a rudimentary supervisory bit. So if you're going to tell me that OS 360 had the protection ring, I could tell you no, it didn't. Because I remember writing programs that all you had to do was set a bit that made your application look like it was part of the operating system, and you could take over the entire machine. So not buying it. So the first release of Multics was in 1967. They were actually trying to use rings to do two different functions. First, the one we were just talking about was to protect the applications from causing the kernel to shut down and take all the applications with it. But they were also looking at the ring structure as a mechanism to allow, like this would be in areas where you had multi-level security, or MLS, where you had multiple applications running in different security levels on the same machine. And this would allow a way for that to happen without an accidental intermixing of those two applications. So they were looking at it from security and they were looking at it from protection. So the innermost ring that they designed held the highest level of privilege. And of course, that would be the operating system. The outermost ring was the least privilege, had the least amount of privileges, and that would be considered the user space. The ones in between were dependent upon whether or not your application was granted to access and to operate at that level. And the idea behind it was that that rings that were of higher security level than yours would be able to see your ring, but areas of the system that were of lower privilege did not have the rights to see your ring. But anyway, even the logo showed the ring level and the doors and the gates in order to gain access to those rings. Some people, I've kind of heard this on different YouTube, and it kind of bothers me. I don't know why, but I didn't work on Multics, so I don't really have any skin in the game. But they say that Multics failed. No, Multics didn't fail. Multics was actually very successful. I think they think that because Bell Labs left the project, and they think it was because Bell Labs felt it was a failure, but that's not true. The Bell Labs pulled out because there was really two reasons that I know of, and I haven't heard anything other than these two. So if you guys know some other reason, great. Let me know in the comments below. That's what they're for. But the ones that I always remember hearing the Bell Labs guys talk about was the Bell Labs managers who were paying the salaries of these guys wanted to know, hey, how long are you going to keep these guys? I have work for them and I kind of need them back. And can you give me a plan as to how long you're going to keep them and what they're going to be doing so that I know what, so when my management asks me to account for your time, I know I can give them an answer. And the Multics team never could because it was a research project and they were exploring different things. But when you're in research projects, you don't have clear goals. I mean, you have, I remember on Plato where we had broad goals, but no specifics on how to get there. That was what we were doing. That's what they were paying us to do, was to figure out how to get from here to there. So, yeah, and that didn't sit well with the Bell Labs management. The other problem that they had was that the Bell Labs had been making requests for some consistency in the environment that would allow AT&T to be able to reuse this code in their environment and take advantage of it. And Multics wouldn't give them an answer. They I don't know if they wouldn't or they couldn't or they just didn't know. But Bell Labs thought, well, we don't really see how this is going to benefit AT&T. And so that was really a major reason why they left. Is that they thought, well, this isn't going to really benefit us. And I really have a hard time telling my manager every week, this is what I'm doing, and he's going to ask me the same question and tell me how this benefits us. And he couldn't give an answer. So, yeah, that's hard to stay on a project when you don't have a reason to be there, right? And you don't have any benefit to be there. So, like I said, before protection rings, when an application crashed, it usually took everything with it. It offered a means to protect, and Bell Labs took what they had learned from Multics, and that would have been Rod Thornton and Dennis Ritchie, that they would have taken that and taken what they learned from Multics and then included it in Unix, and that's what they did. And this is what they did. This model is from Maurice Bach's book. This is called The Design of the Unix Operating System. It's a very detailed explanation of all of the details of Unix and how it was implemented. Something you hardly ever find today in proprietary software. But they chose two rings, and of course in this day it was ring 0 and ring 1. The kernel occupied the system or the kernel space or protected space. And then the user applications ran out in what they called the Wild West or the user land. And there was a mechanism by which user applications could make requests of the kernel through something called a syscall. And a syscall was nothing more than, this is what I want you to do. I want some resources for memory. I want to open a file. I want to read a file. And that's what the syscalls would do. So by the time Unix had reached System 5, there was over 64 system calls that had been created. And only about half of that number was actually in use at any one time. The other 32 just weren't used that frequently. And in fact, when Dennis Ritchie went on to develop Plan 9, he actually reduced that number to 51. It just didn't need that many. But so that's basically the design. Now I have seen some of drawings with this, where the shell is drawn in its own layer. But I think that came from the fact if you look at the way Maurice drew the drawings for the kernel, he wanted to kind of call out the applications in the shell. And I think that his intent was to actually kind of subdivide the user application space a little bit to depict that. That, hey, that you don't have to write all these applications, that we're going to provide some of these with the operating system, like copy and assemble and the compilers and all that stuff. So I think that was the reason why a lot of people think the shell is on its own layer. It isn't really. A shell is nothing more than a user land application. You can write a user application and make your own shell if you want. I mean, it isn't any different from any other application, except that the shell does have a couple of unique things. It can set environment variables that can be used by applications. It can also start and stop jobs and run them, whether in foreground or background. And then it has a scripting language to allow you to do some things to be able to automate tasks in the future, for repeatability and passing parameters and so forth. So, yeah, I mean, there's nothing really too unique about the shell that would make it fit in its own shell of the kernel. You don't have to have a shell to run a program. Your applications that run as system services, they're not running out of a shell. In fact, you'll probably see that if they are using user logins at all, you'll probably see that it says no shell. That's what they're running. So the model kind of evolved when Intel really felt that there was a need to develop one specific for the x86 platform. And so they came up with this. They came up with a 4-ring model. And that used the same two the same two rings as Unix did, the kernel being at ring 0 and the user application being in the outer ring. But they added 2 more. They actually pulled the device drivers and the device access out of the kernel and put it in its own ring. And they felt that there would be some advantage to doing that for performance reasons. Plus, it would offload, they hope, some of the kernel overhead. As it turned out, OS2, I remember, did some work in this area, and they tried to do some of this, and I remember how poorly performing OS2 was at first until they finally decided not to implement this method. Because if you think about it, you've got basically a system call between the user application and the driver access. So anytime you want to access the driver, you have to go through that layer, and then that in turn has to call the device driver, and that in turn may call the kernel. Now, the user application can make direct calls to the kernel as well. It doesn't have to feed up through all those layers, but most of the time it's going to be dealing with the system through the device drivers, right? I mean, I have a terminal, and I have a file system, and I have some devices like a printer and so forth back in the day to be able to do stuff like that. Or I might have had a graphics card that I was talking to. One of the things you'll probably find if you go out and you look at this drawing too a lot, I have modified this. You'll see that Intel says in the yellow layer there, where it says driver access, they list it as device driver. But I think that's a little confusing because it's not really, you don't, I guess you could have device drivers that are running in user space, but I don't know why you would do that. That would endanger the system from a crash. So yeah, more than likely, it was really meant to be a driver access point, someplace to get permission to use the device driver, because if you have multiple applications running on the system, they could stomp on each other. If they're accessing the same driver at the same time, they could clobber the memory, or they could write over memory that hadn't been read yet by the other application that made the request initially. Also, Windows Microsoft had done an experiment with Windows with something called Singularity. And what they were trying to do was to shrink it down, the number of rings to 1. Now, you might think, wait, isn't that Windows 95 and 98? Isn't that what they did? Well, no, not quite. So, yeah, Windows 95 and Windows 98, as you probably recall, didn't have any protection at all. And when an application crashed, chances are it took the entire system with it. The infamous blue screen of death. But Microsoft wanted to experiment a bit with a single layer or single protection ring, and they called that singularity. And they found that, I remember seeing the presentations on it, that it did increase performance of Windows quite a bit. I don't know what they have decided to do with it. I don't know if they're using it. I don't know if they're not using it. That's the problem you have in closed systems. You don't know what they're actually doing. And, that's a shame, but that's the way it is. The Linux standard uses, of course, the 4-ring model, but they only use ring 0 and ring 3. They don't pay any attention to ring 1 or 2. And Windows, by the way, does exactly the same thing. But one of the things I've been watching a few other Linux people that, and I see this and I just cringe every time I see it. There's they mix daemon and Damon together to describe the same thing, and no, they're not the same thing. If you're using the Unix parlance, a daemon is a system service. It's one that runs in userland, and it's usually managed by an external process, maybe systemd, maybe initd, maybe rcd. That all it does is to make sure that it can start, it's been stopped if you need it to be stopped, or if it crashes, it can be automatically restarted again. That's a daemon. A daemon is a device driver, and a daemon has a very set template for how it's written. There's an init, there's an execution, and then there's a teardown when it's done. And there's some levels that it does in order to maintain protection if there are multiple requests coming for the same device at the same time. Not all devices handle that, but some of them do. And that is written into the daemon process to do it. So there's a very specific structure of how to write a device driver, and it's not the same as a daemon. So anyway, enough about that. Linux has, as of 5.8.9, a little over 400 syscalls. I went in and I counted them up. I hope I did it right, but it has to be close because I remember a few years ago it was over 300 syscalls that they had. And I find that kind of interesting considering that Plan 9 only had 51 and only needed 51, and why Linux needs so many now. I don't know the reason for that, and I'm not gonna take a guess as to why, but it does seem like it's an awful lot. Some people say that Linux is too complicated and it's really hard to understand it, but it isn't. It's really simple and it's very straightforward architecture, and it's probably better rather than talk about high-level things like onion. Those are called the onion. Those diagrams are called the onion of Unix and Linux. It's probably look at it in a more conventional block diagrams way of looking at it. So there are basically 3 groups on this screen. There's userland at the top, the middle layer is the Linux kernel, and the bottom layer is hardware. So at the top level, you have your applications, your utilities, and your shell, some things like that, and that is usually running in user space. You might hear it called that. You may also hear it called userland. Both terms are correct. I've heard both of them too. And then in the middle area, you'll hear it as system or kernel space. You might even hear it as protected space, but the only way to interface to that is through the system calls. And you can write, every application is going to generate system calls that generates I/O. If you have a read in a C program, if you have a read in a Python program, it is going to generate a system call to this kernel in order to handle that read. It's got to open the file. It's got to read it. So there's some different areas that I kind of group together, like process management, memory management. There are a lot of system calls inside of those buckets. I didn't call them all out. We wouldn't probably be able to read it anyway if I did that. So I kind of grouped things together into process, memory, file, device, and network. Network normally, years ago, would have been considered a device driver, but the network is really getting more complicated because of the number and types of cards that are available, the type of network structures that are available today. Some of them are really wildly different than the traditional character and block devices. So I kind of moved those out on their own. I think, in my opinion, they kind of need to be moved out on their own. So those would be the component layers. And then the functions that those component layers provide are underneath. Process management is really concerned about maintaining an environment for multitasking. Memory management is looking at managing memory and providing virtual memory to allow applications to continue to run even when they're cycled out of memory in order to wait for another application to run in its place, because you can't monopolize the CPU forever and be able to service multiple processes at the same time. So file systems manage the file directories, the mount points, the files themselves, the reads, the writes, the execute. Even an execute would load a file. So if it's a shell script, or even an application, it's going to get involved with it at some point because it's got to go out and retrieve it into memory. The device drivers are generally where you do device access to get to your printer, to get to your graphics card. Maybe you've got a sound card, or maybe you've got something else, a mouse, a keyboard. They're all going to be in there. And then, of course, the network functions. The next layer down is kind of the support that's offering support to the application software that's running in the user land, and those would be things like who gets the processor next, and then maybe some architecture-specific code like caching, doing branch prediction, and all those kinds of things. Memory management, I'm requesting memory. I want to block a memory. It gives it to me. It also makes sure that if I do write into memory or I read from memory, it's bounded, that I'm not allowed to go outside of those bounds. If my program does, the kernel will boot it out of memory. And then you have, in the file side, you have the file system types, like character or block or stream, for example. Now, stream really belongs kind of in two different areas. I don't have IPC on here, but it also belongs to IPC. It also belongs to network. But the two most common ones, if you look in your dev directory, where you normally see the permissions for the file, you'll see a B for block device and a C for character. Those are the most common ones that you see. And then, of course, you have your device drivers, which are character devices. There are block devices in there as well. I just didn't write it on here. Network protocols, network drivers over on the other side. And then you have that with the second block is really support for the hardware. So the network drivers would be, now some network cards have their own drivers, and some of them require drivers to be in the kernel, but they always require some way, whether the driver is on the adapter or in the kernel, they still have memory that's going to have to be exchanged, right? I've got data that's going to flow into memory at some point. So there is some, it might be rudimentary, but some network cards, like some of the Intel cards, they do their own processing. They handle all the layer traffic, whether it's routing and decoding and sending and receiving packets. They do all that on the card themselves. They don't bother the kernel at all for that until there's data that's about to be transferred. So at the bottom you have your hardware, your CPU, your RAM, your I/O, your terminal devices, your character devices, and then your network adapter. And that really is it. I mean, yeah, there's more to that, and what I want to do in the future is to talk about process management, how that works, how memory management works, how the file systems work, and so forth, and maybe get into networking in more detail. I'm not a network engineer. I know enough to be dangerous. I know enough in order to build my networks, but I'm certainly not a network engineer. I'm not presenting myself as such, but I do know process management and memory management pretty well, and file systems, of course, as well, too. I have written some device drivers in my past. So lastly, I was going to try to bring up the Windows architecture, and I was trying to find anything from Microsoft that I would be allowed to use publicly to depict how their architecture works. I have a image from 2006 that Microsoft published, but it's copyrighted. That probably is out of date anyway. That would be about the time of Windows Vista. And we all know that things changed radically after that, because that was not a very good release for them. I do not have any current architecture for a Microsoft, and I don't have any that I would be allowed to use even if I did have it, because most of that is copyrighted, and I wouldn't do that without permission for Microsoft to use it. So yeah, the stuff I have is out of date. I can't share it. I did check on TechNet to see if there was a link I could provide you to go look, and there's nothing there that I could find. Microsoft has a lot of architectures for specific tasks, whether that be for like IaaS and cloud and using Azure and some of that kind of stuff. But I didn't find anything on Windows 10 as to how the architecture is put together and all that is current. So other than that one architecture slide from 2006. So anyway, that's my problem with closed architectures. It's very hard to get information to really understand how they work. You're stuck in the API with the publish interfaces that they give you. And I remember working years ago in closed architectures where we were trying to get to bitmap mode on one of the machines, and Burroughs had removed the APIs, at least in the documentation, from accessing the bitmap part of the system for graphics. Well, I discovered that they were still in there and they still worked, but I had to go and get the manual from the actual manufacturer of the machine in order to do that. And I don't think Burroughs really was happy that I did that, because for some reason they wanted to do vector graphics. They didn't want to support bitmap, but anyway, they got over it. It was for a customer. They wanted to use bitmap, and so I always try to do what the customer wanted to do. Anyway, that is all I had today to talk about, and I want to take this topic line a little further if that is of interest to you. If it's not, let me know. I obviously don't want to produce content that you guys aren't going to be interested in. Hopefully you found this useful today. If you did, please like and subscribe. And, as always, let's see, I got to get the right mouse here. And if you did find it helpful, and if you have a comment about maybe where to find some architectures from Microsoft that are publicly available that can be used, let me know that too. And we'll add it to the show notes, and people can go and look at that. Anyway. Hope to see you all again real soon, and bye for now.